I'm Ramon Snir from Dynamic Yield. I don't want to sell you on our company. We're generally awesome and we're doing cool stuff. We work with a lot of brands, and what we do with them is very simple, the things you see every day. If you shop on any of these sites, or on Amazon, or in eBay, you will see that a lot of your content that you see is personalized to things you probably want to see. And we also try to make sure that you can reach the products you want to buy without going page and page and page in the category pages. But the issue with my presence here in the conference is that we use a lot of Apache software. We use Elasticsearch for our recommendations. That's how we hire people. That's how we see ourselves. But as you can see from our tech stack, all of these things are very powerful. They can do a lot of things, but they don't do one thing. They're not real time. They're not fast. They can give you very good latency for some things. They can do a lot of computations, rarely, but they will not update your data in real time. They will not give you back, as everyone promised in the keynotes, less than 1 millisecond to get the responses you need. So why do we use Redis? Because it's fast, because it's very easy to train developers to use, and it's plus or minus very easy to scale horizontally, vertically. And the thing that the marketing team of Redis Labs try to avoid is the question of, is Redis a cache or is it a database? And I'll be honest and say that the first time I installed Redis in our production was because we needed to stop hitting our HBase. It took too long, it was too slow, and we needed a cache between HBase and our application. So in the next few slides, I'm going to show why we use Redis as a secondary database, caching stuff. And then we're going to look on why, even though we don't see ourselves as a Redis shop, we do use Redis as a primary store for a lot of things. So the first thing we did with Redis was a cache. Why? It is very easy to set up. It was 4 lines of code in Chef. It is very fast compared to HBase. It shares information between several applications or application instances. And the master-slave replication allowed us to invalidate the cache in one place and to have it replicated to the slaves. So we can read fast from the cache, even though sometimes the writing is a bit slower because we have to cross instances. And there are 2 things I would like to note about using Redis as cache, even though you're not supposed to do that according to Redis Labs. One is expiry is a very important functional feature. You want to maybe set it as a fixed TTL, expire in 5 minutes, because you know this data is going to refresh in 5 minutes. Or maybe you want to set it to expire 5 minutes from now, because it's good enough for the next 5 minutes. And when you don't know how to reason about the timing of when things will change or not, we add an extra parameter to the key of the cache to make sure that when we look up the value, we won't find it if one of the parameters we have is changed. Yes, Redis will store the old values, and that's where we can just have a long TTL to delete the stuff. The other great thing or not great thing, another thing to remember when you're using Redis as cache is bucketing. Redis is very easy to use as a key value store, but it's also very wasteful of memory, and memory is expensive when you're doing everything in memory. And bucketing, which is explained on the Redis website, is not an original idea, means that you store multiple key value pairs in one hash. And since the overhead per key is the large part, you can have 100 pairs inside the hash for lower overhead than having actual 100 keys. Basically the point. And when you scale to Redis on Flash, it becomes even more important, although you do need to remember that the whole hash will move together. The usage changes very slightly. You just change from hset from set, hget from get, and it's not very different for the application. Basically free money if you're paying for your RAM, and you probably are. And then there's the other version of Redis as a cache, which is the indexing. And this is something we do with our MySQL. We don't want to hit our MySQL to read data from it, but we do need updated data from there, and we can't ever miss and hit the MySQL. Our MySQL server is not good enough to ever have a miss that hits it. So what we do is we have a separate application that reads through the relevant tables in our MySQL and sets the values into Redis. So our application only ever reads from Redis, and it never has to actually hit the database. And this basically comes for several reasons. We don't want cache stampedes to hit our database. If several applications miss and hit at the same time, our row will be locked and everything will be sad. And the, of course, awful thing is that when you set up MySQL on your own or MariaDB, and not through RDS or something more managed, it is very hard to replicate your data between data centers. So you manage your application in Virginia. You have to read it also from Ireland for better performance for Europe or Frankfurt. And you, even worse than reading a local MySQL is reading from a MySQL across the ocean. So by indexing the data to one Redis in Virginia and replicating it with the great feature of Redis, which is replication, to Ireland, Frankfurt, Singapore, we can accelerate the reads from going across the ocean to reading from a local Redis in the right data center. Today, we don't use Redis as a cache today in production, which is the good news, but we still use Redis in several places as an index. Because that's something that we found that Redis is really good at and we couldn't replace. And we still love MySQL for various reasons. The next few use cases are things that we do with Redis as a primary store. Some of these make more sense, some of these make less sense. And all of these use cases exist not because we planned it to be on Redis, but because we had an issue and we had to get the feature out. It had to be fast, it has to be cheap, and it has to meet the functional requirement of being fast enough for our customers. And the first very common use case that Redis has is managing user profiles. You want to keep for a user how many page views he had, maybe which page views he had. You want to know what he clicked, what he bought, what interactions he had. This is data that changes very frequently. You get random users coming into the website. They do a few interactions, and you need to immediately start personalizing for them. You can't wait for an hourly aggregation or even a 10-minute aggregation. The data is very sparse, so it's bad for a lot of things. And there are a lot of small users that come in, do one action, and disappear. So you can't assume that your users are going to be interesting. We started off when we had very little traffic with HBase. As I said earlier, it was very slow at random access, although it's very good at other things. And the latency wasn't even consistent. So even if we could say that it takes 15 milliseconds, we would see times that it took 100 and 200 milliseconds, which is just not acceptable. So the easy solution was, as I said before, stuff it into Redis. Every time you want to read something, check if you can put it in Redis first. And at least you stabilize the performance for your most frequent visitors. Visitors that come often, you know that they'll be in the cache. But RAM is expensive, and you don't want to keep your entire user profiles in the RAM, because who has the money for it? We all have to remain profitable. So what we decided to do is only keep the hot data, things that is recent from the past 24 hours in Redis, and put everything else somewhere else. We chose LMDB, which is short for something, L is lightning. Every day we have an aggregation with our Spark that builds these LMDB files. It propagates them to servers that serve it very fast. But since we can only update these files every 24 hours, we need something else in the middle. And that's where Redis comes in. And basically, when we meet a person, we read its profile from two places. we read it from the LMDB. We read it from today's data on the Redis. Since everything here is counters, we can just sum up the vectors, and it's very easy. If it was anything that's not counter-based, it would have been a mess to sum it. Yeah. But one thing that, of course, we noticed during the design phase is it's now 12 a.m. and 5 minutes, and the Spark aggregation is only going to finish in 3 hours. So what we have is that we keep the user profiles in Redis not for 24 hours, but for 48 hours. And until we see that the Spark finished updating that last bit, we take the data from LMDB, add it to the vector from yesterday and from today. That way we have a full picture from beginning to time to 2 midnights ago, and then to this midnight, and then to actually now. And I put a small link here. We do use time comparisons with just the Unix epochs, and we're optimistic that everything will be fine in real life. But you're welcome to read this blog post telling you why using time is not that simple. And key expiry, we use it a lot, not just because RAM is expensive and we have to clear things up, but because when a key expires, it means something. When we don't see a key in Redis, it means there's no data on it. It means that whoever wrote it originally knew that at this point of time it won't be relevant anymore and it shouldn't be counted on. Even though Redis might not free up the memory, when it reads the data, it won't return you data that is stale. So you can rely, plus minus timing issues, on the expiry of keys. And it's also very cheap. Actually, the most famous way to clear a database without actually flushing everything out is to have a loop setting expiry to your keys. Deletion is very costly in Redis, but setting an expiry to a key is very cheap, and Redis will handle it asynchronously when it is reasonable to do it. And going back to our buckets from before, since we bucket a lot of our data, we have to remember that the expiry is on the key and not on a specific pair in the hash. So we need to make sure that whenever we bucket something, we account for the expiry, that all the things in the bucket reasonably will expire at the same time. And about updating the user profiles. We saw an example, I think, it was in the keynotes, of comparing whether you want to use the whole fire hose with our Redshift and everything going and eventually reaching Redis, or do you want to actually straight write to a Redis? And we'll admit that sometimes we use this, sometimes we use that. The advantage of writing directly to Redis is that it's faster. That means that once you update, other clients can immediately read and see that it updated. And it means that there are less points of failure in the flow. But it also means that if that failed, you don't have any way to deal with it. If you couldn't write to the Redis, you can try again. That might mean you did it twice, which is maybe not so good. So for some use cases where we need the stability and don't need the latency from write to read to be so much, we use a queue. Kafka and Flink are two technologies that we love anyway, so it makes sense. It's stabler, meaning less things fall between the cracks. It means that a lot of writes won't damage other writes because we can throttle things. And it is easier to scale for writes because we can set up simply more brokers, more backlog, and write things when we can. And another thing we have with the user profiles is that we don't want to waste memory on those user profiles. We have a lot of data. And putting it as a plain JSON string or as a hash per user is very expensive. Hash per user is expensive because we lose all the benefits of bucketing. And JSONs mean you have to read and write everything and hope that everything you do is safe. So what we do is we have, for each user, in the value of the hash, we have message back value representing the vector of the data on the user. And we use a very nice feature that Redis has, and I think wasn't mentioned enough in the conference today, which is Lua. These are things I mentioned. We generally love message back over JSON or anything else because it is so much smaller and so much cheaper. Our bank account loves it. We love it. It's generally great. There are a lot of libraries in every language to use message back. And since the increment has to be atomic, we can't read the value, update the message back, and write it back. What we need to do is to use Lua. So when a user makes a purchase and it needs to update 4 values in the vector, what we do is we execute with eval SHA or regular eval a Lua script, and we give it the identifier of the user. We give it what it has to increment. And then Lua does it. This is the only time we'll show code. The screen is actually large enough. But it's really simple. It's basically what your application would do, just in a not so pretty language, and atomically. It reads the hash, it sums up the vectors, and it writes it back again. And it sets expiry just because expiry is always good. This means that, one, that we don't have to have the logic on how we sum vectors in the applications, which are in 2 different languages. And it also means we can trust this to be atomic, and we can keep using message back and bucketing without re-architecting everything. It's not super exciting code. Another thing we had was that we were brought the requirement of doing what Booking.com are very famous for. 240 people purchased this product in the past day, or so many people viewed this product in the past week. And the issue with this feature is that you can't just increment the value. If the same person came back to the same product trying to decide if to buy it or not, that's still one person. You can't increment the value every time the person watched it. You have to know how many people watched it. And April 22nd, 2014, Salvatore added hyperloglog as a first class member operation, which means for us that we can just reuse this in 10 lines of code and do everything that we need. So we have a lot of hyperloglogs for different time frames and different time resolutions. So we would have, it's actually Wednesday. So we will have, for this nice jacket, time resolution of hour, Wednesday 4 p.m. This is my social security number. That's one person who viewed it. Similarly for the day, April 25th, one person viewed it, week, and so forth. And the good thing about this is that when a person comes back in again, we still run the same commands. We don't care that it's the second time. And the hyperloglog data structure will make sure plus minus, I don't know what the official number is for the error, but we treat it as 3%. Plus or minus a few percentage of errors, it will keep track of how many actual people saw this. Since we want a rolling window, we don't actually read the day resolution when we want to know the day. We read 24 hours. So we will read from yesterday 4 p.m. through midnight until this 4 p.m. And pfcount knows how to aggregate these values, deduplicate as much as possible repeat users, and give you the number of actually how many people viewed this product or purchased this product or whatever else we need. This is a project of one day, without aggregations, without anything, that Redis just made possible. The next use case is either the best example or worst example of why we have Redis in production as the secondary or second primary database. This was an emergency we had to deal with. We needed to work around it. What happened was that we couldn't use HTTP to call from one application to another internal application for very bad reasons. We could have done a lot of things to solve it, but none of them would have helped us in the time frame we had of 1 week. I'm not proud of this, but Redis saved us that 1 week, and it works very well. So basically, when you usually use HTTP, you have one client with several servers and a load balancer in between. And when the client makes a request, the load balancer will pick a server that's available and passes the health check and everything. The server, the server will reply, go back to the load balancer. The load balancer will give the response to the client. But we couldn't use HTTP, and we needed something fast that both, in that instance, Node.js and Python can work with, that doesn't require actually fixing the problem. So we used two features of Redis. One of them is lists as queues. Because there wasn't anything better, we used the lists. Maybe today we would have used streams, but that wasn't there. And we use PubSub, the publish subscribe. Basically, what happens is that we need to make a request. The client subscribes to a dedicated channel, which will have the response. So it subscribes to a channel called response, and then this random number. And it puts in the queue a request. Please answer to this channel and answer to this question. It sends this to Redis with the regular client we have. And then as many servers as we have in Python can do blocking write pop from the queue, find a job they have to deal with, do whatever they need to do, and publish the response back. The client then receives the message and can finish this whole thing. It wasn't a good thing to do, but it took 1 day to do. Instead of telling the customer that it's impossible to fix or that it will take time. Still live in production, by the way, not proud of it. Another use case we had to deal with was that we needed to do recommendations in emails that our customers send out. So you get an email from Urban Outfitters, and it tells you, hey, good morning. Have a great day. It's going to rain tomorrow. Do you want to buy one of these jackets? And the decision on which jackets we want to show you is not a decision we make lightly. It's a decision we make for each person based on what we know on that person, as much as we know. Because the goal is to find you the jacket that you want to buy and not show you the wrong jacket or women's jackets or men's jackets. We want to show you what you need to see. And another thing we want to do is to make sure that if we send the email in the morning, but you only got around to reading it at 3 p.m., we want to use those extra 6 hours of data, which might have affected your user profile. So we don't want to embed the images when the email is sent. We want to choose the right image when the email is opened. And another 3 requirements we had were when the slots, the 4 images for 4 products can't repeat themselves. And when you reopen the email again tomorrow, you're probably opening because, oh yeah, I got the jacket yesterday, I want to buy it. We can't recommend you again different products. We need to remember what we recommended you yesterday. And of course, we need up-to-date pricing because otherwise we're lying to you, and that's not okay. So basically what happens is that when you open this email, I think that's Gmail, it reaches our servers in 3 requests. And these are potentially 3 different servers that just got the request through the load balancer. Each request needs to give you back an image. And as we said, that choice of the image has to be done with the thought of what other images we're going to show you. And it has to check if we already showed you something in the past. So the first thing we do is, of course, we look at the decision store, which is Redis, because we need to be fast. And we check, did we recommend this person for this email products already? If so, we find the right image. If this is the second slot, last time we showed these shoes, we'll show the shoes, and that's easy. If not, we need to call an external server to make the actual choice. But these are now 3 separate application servers that are calling one recommendation server. And they need to make sure that they, 1, don't waste the recommendation server CPU time by making 3 requests. That's wasteful. And that they get the same consistent results, that the order doesn't change, because if this one thought it was showing shoes and this one is showing shoes, it's not good. So what we have is we have a lock per user. We're not using redlock itself for various reasons. But we are using locks in Redis to make sure that only one of these servers actually makes a request to the recommendation server. That one server obtains the lock, makes a request, and gets back the 3 products that we should recommend. It stores them in the decision store and returns the image. And now when the other 2 servers see that the lock was freed, they know the request was done, and they know to look in the decision store to see what they need to recommend. They won't make the same request again to the recommendation server because they don't have to. They'll just return the image. And joining these 2 stores for the lock and for the decisions, also the settings on how the widget is supposed to be built also need to be very fast for the decision to be made. And they're, of course, in a Redis index that we talked about before because we don't want to eat the MySQL. And we also have an index for the relevant products because we need to know where is this shoe, how much it costs, and we need to know this fast. And there is the recommendation engine itself that we, of course, potentially could call 3 times, but we make sure not to. That's it, pretty much. Does anyone have questions?
Thank you. My question is regarding...
Can you just speak up?
Hello.
Thank you.
So I think you mentioned high availability and you mentioned Lua script. So my question is kind of linking the both. With Lua script, does high availability work out of box or do you have to do anything?
The Lua script is basically a Redis operation that you can better define. It is very similar to defining a new operation through Redis modules. Okay. I'm not sure.
So if it's just an add-on to the module, so in that way there is no special thing required for replication.
So what happens with Lua is there are actually 2 modes now, but back then there was only 1. When you ask the master to execute a Lua script, in the original mode, it also asks the slaves to rerun the same Lua script to make them consistent. You gave it the script, you give it the parameters, it runs it, and it also puts in a replication log for the slaves, the same request to run the script with the parameters. It's run in between the same operations as it did in the master because Redis is synchronous or serial, and then all the slaves do it too. In the new mode, if what you do is stable, doesn't use anything random or anything weird, it will replicate the changes that the Lua script did. So if your Lua script read a value and set a value, you don't need to tell the slaves to read again. You just tell all the slaves, write this new value. So if there's a failover, they have an updated state after the Lua scripts ran. Yeah?
Yeah, good. Thank you.
Any other questions? So I'll just say a few more things that are not in the slides. We started originally, we were using the regular Redis. We downloaded it from the website, or it might have been through a package manager on CentOS. And we had multiple instances of Redis for different use cases. In some of them, we used different databases just to make the key spaces make more sense. And then after a year and a half, we had scaling issues. Not for high availability with Sentinel, but actual scaling. We tried out Redis Cluster open source, which we deemed not stable enough in its first release. It has gotten better. And then we used Redis Enterprise Cluster. Back then, it had a different name. And that allowed us to very easily shard the data in a mostly consistent way, and also to still maintain the replication between 2 data centers. As you can do replication with open source Redis, with a master and slave, you can also set clusters in Redis Enterprise to be master and slave, so that the entire thing is replicated. Not so much for failover. You wouldn't, I mean, in theory, you could have the whole data center crash and read from the other one, but mostly so you can read from a different region. And after even that couldn't work enough for us, luckily enough for us, Redis Labs released Redis on Flash, which allowed us to create even bigger shards with even more data, and still fast enough for everything we needed. Can you just?
Redis Cluster?
I'm sorry.
What are the issues you face in open source Redis Cluster?
With the open source cluster.
Yeah.
So when I evaluated the original release of Redis open source cluster, I saw several things. One is something that wasn't fixed until today, just because Antiris doesn't see that as Salvatore as a priority, which makes sense, is that it assumes that all of your nodes or shards are in the same data center or even rack. It doesn't know that it has to make sure that this master and this slave are not on the same instance, because when the instance falls, you lose both versions. And it also doesn't know that when you want to read something, you want to read from something that's nearby. It assumes that all the replicas are equal and that all the nodes are independent. So that was one issue we saw simply with the design of Redis cluster. Another issue we had was probably just a bug, that after 2 hours of playing with it and making issues, it just got stuck. And we had to shut down the whole cluster and raise it back, which we thought was a bad sign before going into production. That was it. It works. It just it wasn't stable in the first release, and it missed one feature we needed.
Any other questions? Awesome. Thank you for the chat today. And